Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This presentation is an introduction to the MicroPython installer on the Arduino GIGA R1 WiFi board for the development of MicroPython scripts. The Arduino GIGA R1 WiFi board is a powerful, feature-packed microcomputer with a large amount of general-purpose input-output GPIO pins and dedicated connectors. The board will run MicroPython scripts if it has been flashed with the corresponding interpreter. This presentation examines the installation of the interpreter using a utility application from Arduino Lab. After flashing the board with the MicroPython interpreter, some very simple demonstrations of MicroPython scripts are shown. These examples are very elementary. These examples are meant to introduce you to navigate the pin diagrams on the board. There are two groups of mnemonics for pin nomenclature, one for Arduino and the other for the STM32 CPU. For the MicroPython demonstrations, all references to the GPIO pins will use the STM32 conventions. To be productive in developing and running MicroPython scripts, one should use an integrated development environment or IDE. There are three options for the IDE. Thonny is a lightweight editor for Python scripts. It is a simple way to help you write and debug your code. Since it does not have too many bells and whistles to distract you from programming, you can get your simple Python scripts up and running quickly. Arduino Lab for MicroPython is a pre-release editor for Arduino boards that support the basic workflow like connecting to boards, uploading code, managing files, and interacting with read eval print loop REPL. OpenMV is best suited for vision applications. Since it has many features, it is best to cover this topic in a separate presentation that will permit a slightly more drill-down review. The GIGA board must be flashed with the Python interpreter to run scripts. And instead of messing with command line operations to perform this operation, you can use an Arduino Lab app called micropython-installer. It is a good idea to reset the GIGA board before flashing the MicroPython firmware for the first time. After turning on the power to the board, press the reset button twice in rapid succession. The green status LED will start to fade in and out slowly, indicating that the board is ready to receive a new interpreter. The next step is to flash the board with the MicroPython firmware as shown after the slide. Programming with an integrated development environment, IDE, makes it easy to keep scripts in manageable folders and to deploy these to the board. In this tutorial, we will use Arduino Lab for MicroPython to accomplish most of the tasks. However, you may wish to evaluate the other two IDEs also so that you can choose what works best for you. Take a quick look at resetting the GIGA board. The reset switch in this diagram is on the top left-hand corner. If we turn the board around 180 degrees, the reset switch is now at the bottom right-hand corner. When we turn the power on to the board, the RGB LED cycles through the three primary RGB colors until we go and press the reset button. We have to press the reset button successively in quick succession so that now, instead of cycling through the colors, the green LED light fades in and out. In this section, we will download the Arduino MicroPython installer from the Arduino website using the wget command in a terminal window. The URL for the installer file is shown above. This URL is subject to change with newer releases of the installer. Once the website acknowledges the URL, the download begins. After the download is completed in a few seconds, check the folder for the size of the downloaded file. Of course, you should validate the checksum of the deb file, but I've omitted illustrating that step here. Then proceed to install the file using the sudo apt command with the install option and the file name of the deb file. Let us go ahead and download the firmware too, even though the MicroPython installer can perform this operation. Once again, we use the wget command and specify the URL for the firmware, which is subject to change with newer releases of the firmware. You can validate the downloaded firmware using its published checksum. We will use this firmware file to illustrate the flashing with a custom firmware. That is the only reason for downloading this firmware in this demonstration. To install the MicroPython installer, enter the sudo apt command with the install option and the name of the corresponding deb file. Since I had previously installed the package, the screen illustrates this fact that the installer is already installed. For Ubuntu users, click on Show Apps at the bottom of the left nav pane. Scroll through the app icons until the icon for MicroPython installer is visible. For first-time use, it would be a good idea to pin it to dash for future frequent use. The icon disappears from the initial position and will now be visible in the left nav pane. Select it to launch the installer. In due course, the landing page of the app will appear on the screen. An alternate way to launch the app is to enter the command micropython-installer at a prompt in a terminal window. In addition to displaying the landing page, the method uses the terminal window to log text output from the app. If a board is detected by the installer, then its corresponding icon image is displayed in the upper half of the landing page. The lower half of the landing page is used for the installation of custom firmware. If no board is detected, then the connected board should be reset by pressing the reset button twice in rapid succession. The green status LED will fade in and out slowly if the reset is completed successfully. Select the Install MicroPython button in the middle of the landing page. The app will select the appropriate firmware for the detected board and flash it to the board. While limited status information scrolls on the landing page, if you are using a command line to launch the app, you will receive detailed log-style information on the operations by the app. Once the flash operation is complete, a green status LED stops blinking. You may remember that during the download section earlier, we downloaded the firmware too. We really didn't need to, but in order to demonstrate the use of custom firmware, that download comes in handy. In the lower half of the landing page, you can drag and drop the firmware or browse to select a firmware. The app will flash the firmware to the board. It is good practice to reboot the board after the flash operation is complete. After the board has been flashed, it is always a good idea to validate the operation. After flashing, the board is visible as a storage device under File Explorer. There are 4 files under the root folder of the board. If these 4 files are visible, then the board is ready to run MicroPython scripts. The file boot.py contains initialization routines for USB and file system associated with the board. The 2 key libraries are loaded after the board boots for MicroPython scripts. These libraries are machine and PyB. The file main.py runs under user app code that the user may want to run upon boot. The readme.txt file explains the separate roles of the boot.py and the main.py files. Since the Arduino Lab for MicroPython is still in pre-release phase, the version shown in this demonstration will inevitably change. However, the home link will not change perhaps until version 1.0 is released. For Linux users, IDE is extracted from the download archive file format. Then the executable is run without any further installation steps. There are two main windows in the IDE apart from the menu and toolbars. The top window displays the current Python script. The bottom window displays the interactive output during the running of the script. The bottom window is under the run eval print loop or REPL paradigm. You can type Python statements and receive immediate response from the interpreter in the bottom window. Navigate to the website for the Arduino Lab for MicroPython. The link is in the notes to this tutorial. There are 3 versions of this application, one for each of the top 3 operating systems. In this demonstration, we will use the Linux version. Click on the corresponding link at the website in the middle of the page to permit the download of the corresponding zip archive to your downloads folder. After the download is complete, locate the file in your downloads folder and right-click it to proceed with the unzip operation. The operating system places the unzip file under a corresponding folder. Locate the file in this folder and right-click the name to change the properties of the file. Enable the file to be executable as a program. You can now launch the file to run Arduino Lab for MicroPython. When the IDE loading is complete, it will not be connected to any board. Therefore, the status bar at the bottom of the window will indicate the status as disconnected. Before we proceed further, take a look at the version number for this IDE. From the main toolbar, navigate to the About menu under the Help button. The current version is still not 1.0, which generally means that it remains under initial development. Click on the Connect button on the main toolbar and select the port for the GIGA board. If you are unaware of the correct port, then disconnect the GIGA board to determine which port is no longer active. Turn on the GIGA board to check which board becomes active. This is the simplest way. Once the board is connected, summary information from the board is displayed in the bottom panel. Click on the Run button in the main toolbar to run the sample code. The lower pane will identify the firmware and the board's CPU. You can enter commands in this pane for the IDE to interpret. After the GIGA board has been flashed, the mass storage resource for the board appears under File Explorer as a 16 gigabyte device. By default, there will be 4 files with boot.py and main.py being of primary interest. Boot.py runs when the device is loaded. The recommendation is not to edit this file. Main.py runs after boot.py has run successfully. Any code that needs to run immediately after the device has been loaded should be embedded in this file. While the MicroPython platform for Giga has many modules, there may be a need for additional modules. The methods to install extra modules will be examined later. The Arduino GIGA relies on STM32H747 microprocessor. There are differences in pin nomenclature between this microprocessor and the common Arduino conventions. One cannot choose which CPU to run MicroPython on the Arduino GIGA R1 WiFi board. MicroPython automatically utilizes the dedicated Cortex-M4 core for its execution. This is by design, as the M4 core offers several advantages for running MicroPython. Lower power consumption. M4 is a more energy efficient core compared to the M7, making it ideal for battery powered projects where minimizing power draw is crucial. Simpler architecture. The M4 core lacks complex features like caches and floating point unit present in M7, simplifying the MicroPython interpreter and potentially improving its stability. Dedicated resources. MicroPython has exclusive access to the M4 core, ensuring smoother and uninterrupted execution of your scripts. While the M7 core isn't directly used by MicroPython, it remains available for other tasks. One can program the M7 core using Arduino C++ code to handle more demanding operations alongside the MicroPython scripts. This dual-core architecture empowers the GIGA R1 WiFi for complex projects requiring both efficient scripting and intensive processing. Here's a summary of the CPU usage. MicroPython runs exclusively on the Cortex M4 core. Arduino C++ runs on the Cortex M7 core. One doesn't need to choose which CPU to run MicroPython on the GIGA R1 WiFi. MicroPython seamlessly leverages the M4 core while leaving the M7 core free for one's custom C++ code, offering the best of both worlds for versatile and powerful projects. The two demonstrations in this presentation are temperature and humidity readings using a DHT22 sensor and distance measurements for conditional action after receiving the data. There are hundreds of articles on the use of these sensors. It is not the intent of this presentation to discuss the technical aspects of these sensors. The main purpose of this presentation is to help you become comfortable in using Arduino Lab for MicroPython for your scripts. The DHT11 and DHT22 sensors have been in use for a very long time. The low cost of these sensors with reasonable accuracy in data acquisition permits their use in many industrial applications. These sensors are not limited to lab experiments. The minimum sample interval for DHT11 is 1 second, and for DHT22 it is 2 seconds. Rob Tillard has provided tremendous support for these sensors through continuous refinement of the corresponding libraries. However, for MicroPython use, there is a basic library called DHT that offers the basic support for both sensors. This library is used in this demonstration. The days of programming one's own library for DHT support are long past. Take a look at the protocol to have a better understanding of one-wire data communications, but please spend your time on extending your applications rather than rebuilding yet another library unless you have a very special reason or skillful interest in such an effort. Let's take a look at the pin diagram of the GIGA. For the DH222 temperature sensor, we're going to use the D23 Arduino pin, which maps to PG13 as shown in this diagram. It's the top view, second from right, last row. The assembly on the breadboard looks somewhat like this, with the pull-up resistor between the data and the positive feed set at 4.k ohms. When we assemble this in the real world, it gets a little messy because of the DuPont connection wires, but I hope you can see that the diagram has faithfully followed the breadboard layout. So looking at it from different angles in here should give you an idea how we're connecting the sensor to the GIGA. Here is the temperature sensor demonstration. We have a file, and it's just a basic test script where we import the libraries, DHT for the sensor, machine for the board information, and time to install a delay of 2 seconds for reading. So we instantiate the sensor by calling the library and telling it that it's a DHT22 sensor. Notice that we're using the CPU pin number PG13 instead of the Arduino pin number, which is pin 23. We just put a little header in case you want to use a CSV file to extract the data, and then put an indefinite loop and start reading the data by calling the method for the measurements. And then we read the temperature and the humidity in separate calls and print the value on the screen. This is as simple as it can get, and then we have a 2-second delay because it's a DHT22 sensor, and we repeat the process again. So let's go ahead and run this by clicking the run button, and you'll see it immediately starts running and starts displaying. I have intentionally put a timestamp so that in case the values for temperature and sensor don't change, you will still be able to see that something is being output. This is the Unix epoch number. Just don't pay attention to it as far as this demonstration is concerned, but you can see the temperature is 24 degrees and the relative humidity is 35%. Now we can stop the program by clicking on the stop button, and then just to demonstrate that the bottom pane is indeed interactive, we can go ahead and type some commands, in this case a print statement, and you see it reads out the value of the variable that was last presented to us. And you can perform any other operations too. It doesn't necessarily have to be related to the script that you've run. And at the end of this, we can save it by clicking on save, and depending on which folder we set it to, we can either save it on the desktop, which is what we've done in this case, or we can save it on the mass storage device. Most of the older Arduino boards have a single status LED that has the mnemonic LED underbar built in, and the pin number is generally 13. The GIGA has 3 LED devices, red, green and blue. This demonstration is the simplest example illustrating their use with the help of a low-cost distance sensor, HC-SR04. Again, bypassing comments on the accuracy of the sensor, since ultrasonic sensors are cheaper than laser time-of-flight sensors but less accurate too. We use a simple if-then-else clause to display the 3 different LED devices individually. Take a look at the code to understand how the mode for each of the applicable pins are set. 2 modes for the ultrasonic sensor, trigger and echo. 3 definitions for the RGB LED status devices. Here is the breadboard schematic layout for the ultrasonic sensor test. We're using all 4 pins. The power and the ground are flanked on the outside, and the trig and echo are inside. And the trig and echo go to D8, D9 as shown in this slide. Take a look at the picture and you will notice that there is no intermediate component. It plugs in directly to the GIGA from the pins. Let's go ahead and launch Arduino Lab for MicroPython. We navigate to the folder where the executable resides, right-click, and run the app image. In due course, the UI for Arduino Lab for MicroPython is launched, and we have the test example for this ultrasonic sensor. You'll notice traditional import statements for machine, PYB, and time. These are very common ones: machine for the pin settings, PYB for some other settings related to the sensor, and time, of course, to have a 2-second delay between the calls. So let's look at the class definition first for the HCR. It's really not necessary, but in case you have multiple ultrasonic sensors, this does come in handy in terms of triggering the right ultrasonic sensor to measure the distance. When we run the program, the output shows up in here, but more importantly, what I'd like to show you is a very simple example of using a board to block off the distance. And so the light changes from red to blue to green as the distance of the board from the sensor increases. If we bring the board back slowly, you will notice that the light will change from green to blue to red. And this is not so much to illustrate the ultrasonic sensor as much to indicate to you that Arduino Lab for MicroPython is indeed working, and hopefully you'll be able to do some more exercises. This tutorial was a basic introduction to the Arduino Lab for MicroPython. Use the MicroPython installer to flash the GIGA or any other applicable Arduino board to work on MicroPython code. It'll always be a safer route than using DFU util on the command line, even for custom firmware. Both the MicroPython installer and the Arduino Lab for MicroPython are in the pre-release phase. In other words, there will be frequent updates, and therefore links in this presentation will be superseded sooner rather than later. You should try to use the latest version as far as practical. Remember, the best is yet to come. That's all, folks. Please provide feedback in any which way you can. This presentation was prepared with assistance as noted on the slide. My apologies if I have unintentionally omitted anyone or any resource. A very big thank you to y'all. Come back to the channel soon.